Hello, this is Jack Jackson again. We're back with looking at this GeoGebra sketch that I have introducing the derivative and the difference quotient and symmetric difference quotient. In our last video we mainly talked about the difference quotient, and this video is going to focus on the symmetric difference quotient. So once again, I've got the same function I used in my last video, and notice you'll see it here given by this formula. This particular one is 1 over 20 times x minus 6 times x plus 4. You may notice that when x is 0, crosses the x-axis. When x is 6, also there, crosses the axis when x is negative 4. So those are the x-intercepts, and of course the only y-intercept is at the origin. And this thing goes up and down a little bit. We're interested in focusing in on a particular point where a, or x, equals 4, and that's this blue dot here. So let's zoom in on that a little bit, and we'll pick up. Keep zooming in a little bit here, and we're really interested in what's happening really close to that particular x value. Okay, so we have our function there. Now, when we did the difference quotient, we saw that what we would do is we would take a point that was nearby. We'd move over some distance h, like for example right now I have h equals 1, and so we would move over to the right 1. You can see that by this red distance here, and then we would find the point on the curve a plus h, f of a plus h, and then we would find that secant line going through those 2 points. Okay, let's see if I can make that show up. There's that secant line. With the symmetric difference quotient, what we do instead of using the point of interest and a point nearby, which could be on the left or right, we're not going to use the point of interest. We're going to go equal distance to the left and the right. So if you look at this vertical line here when x is a, if you say a plus h, you're on this vertical line and seeing where that crosses the axis. With an equally spaced out vertical line over here at x equals a minus h, we see where it crosses the graph. So note the orange and green points are equally spaced horizontally from x equals a, but not necessarily evenly spaced vertically. So the blue point is exactly halfway between the green and orange points horizontally, but in this case notice it's not even between the 2 points at all vertically. Now, so that gives the points a plus h, f of a plus h is the green point here on the right, and on the left we have this orange point, a minus h, f of a minus h. So in our particular case, h is 1 and a is 4, so that makes the x-coordinates of the orange point 3 and the x-coordinate of the green point 5, and then plug those in the formula here, and this is rounded off to 2 places, but we get y's of negative 3.15 for the orange point and negative 2.25 for the one on the right, the green point. Now we're finding a slope between those two. That is the slope of this secant line, and let's go ahead and turn it on where you can see it. That secant line there is a line we're talking about for a symmetric difference quotient. Now, vertical change is from here up to here, so it's between these 2 vertical lines, that distance, or in other words, how far we go up from the orange to the green, or down, as the case may be. In this case it's up. So we have a positive delta y. With delta y, of course, will be f of a plus h minus f of a minus h. And I think I have that somewhere right here, dy, delta y, f of a plus h minus f of a minus h. It's approximately 0.9 right now. Maybe exactly 0.9. dx will be twice whatever h is. So when h is 1, we get twice that. And so notice we have a distance from h, from the orange point to this, where the blue point is horizontally, and the same distance h over to where the green point is, so it's 2h. So this time delta x is not h like it was in the difference quotient, it is 2h. And so when we divide those two, we get the symmetric difference quotient. So that gives us this formula. So for the symmetric difference quotient, that gives us this formula here. F of A plus H minus F of A minus H, and then we divide by A plus H minus A minus H, which is just 2H. And of course, that's a slope between those 2 points on either side. So this is a symmetric difference quotient. And it's the slope of the orange secant line right here. Now, the point of all this, as we saw with the difference quotient, is that we want to now let h get smaller. And look what happens in the graph. As h gets smaller, both the difference quotient and the symmetric difference quotient get closer and closer to the derivative. So what's happening here, if you look at the lines here, well, let's look at the points here. H is getting smaller. So h is getting close to 0. The green and orange points are getting closer to the blue point. They're coming in towards each other. They could even be on the other side of each other, but they have to come in and get closer and closer to each other. All closer to that blue point. More importantly, the orange and green secant lines are getting closer and closer to the pink tangent line. And most important of all, for the derivative, the slopes of the orange secant line and the green secant line are both getting closer and closer to the slope of the pink tangent line. You can see the numbers. Maybe you're focusing your attention on the lines right at that time. Now focus your attention over here on these numbers. In this table you'll see h. Here you'll see which of course h is delta x for the difference quotient. There's delta y. Divide the two and you'll get this difference quotient. Here you'll see twice h down here in the blue background, which is delta x for the orange secant line. For the symmetric difference quotient, here you'll see what delta y is, and divide those two, you'll get the symmetric difference quotient there. The actual derivative at the moment, the way I've got it set up, is 0.4. So you should see those as I let h, so h start out here, let it get closer and closer to 0, and you should see those, both the difference quotient and symmetric difference quotient, getting closer and closer to 0.4. Okay, we're really close now on the symmetric difference quotient. Okay, now also notice one final thing. The symmetric difference quotient is actually a better estimate of the derivative than the difference quotient is for a particular h. So notice that the slope of what we're looking at is the slopes of these lines here. So we're comparing the slope of the orange secant line to the pink tangent line. They compare their slopes, and we see the slopes are closer there than they are between the green secant line and the pink tangent line. And so, in other words, the orange one is closer to being parallel to the pink one. The slopes are closer to being the same than the green and the pink. And this is usually true. So in a normal sense, most of the time, the symmetric difference quotient is a better estimate of the derivative than the difference quotient for a particular h. And in fact, it is the symmetric difference quotient that's built into a numerical derivative on a TI-84, for example. And of course, you can see that in the numbers over here as well. Right at the moment, the difference quotient is 0.78. Symmetric difference quotient is 0.43. The actual derivative is 0.4. Now, let me continue on very quickly with this. Well, the symmetric difference quotient is an average rate of change over an interval, but notice that that interval has as its midpoint, the x interval has as its midpoint the x value of interest. It is a slope between 2 points on the curve, again on either side of the point of interest. The difference quotient is also an average rate of change, between 2 points on the curve, but one of those is the point of interest. The point of interest is at the end point of the interval. Otherwise, the symmetric difference quotient and the difference quotient are basically interpreted the same. They're both average rates of change. They're both slopes of secant lines. And they're both used to approximate the instantaneous rate of change, the slope of the tangent line, which is the derivative.